Hello everyone. In this lecture, we are going to see how to design a column against buckling. How to design a column having 2 or more diameters.
Welcome to part 2 of column design. Okay. In part 1, we covered thickness calculation of a column due to various load like internal pressure, wind, and seismic. Okay. In this part, we are going to see how buckling can be calculated, how to calculate whether the column is going to fail due to buckling. Second thing, what we are going to see is how to design a column with having 2 or more diameter. The diameter is not uniform. If it's changing, then it might be connected with a cone. What are the types of additional loads which might be there? The discontinuity stresses at the cone, how to design that. Okay. And then deflection, how to calculate the deflection of a column. Okay. And wind induced vibration. These are the topics which we are going to cover in part 2. Before we start, if you remember, we asked one question, okay, and that was related to the allowable stress. When we calculate the thickness by using wind and seismic, I mentioned that we can increase the allowable by 20%, and that is as per 23D of the code, ASME Section 8 Division 1, right? So the question was, in normal cases, we only allow the stresses up to allowable stress. Okay, we keep within that. But when wind or seismic comes into picture, we allow by 20% more than normal allowable. So how it is possible? How we can allow for wind or seismic more allowable than the normal pressure and temperature? The reason is, I hope you have found and you at least put some thought. Okay. So the reason is that the wind and seismic are actually occasional loads. Okay, that is the first reason. They are occasional load and they are expected to be coming even 1 or 2 times in the lifetime of the the tower or column, right? So for these occasional loads, we permit little higher allowable because they are not continuous load. Okay, so that they come under category of occasional loads. The second point is that the stresses induced due to wind or seismic, they are bending in nature. Okay, we calculate bending stresses. So bending is slightly secondary in nature. So even if you allow little more stress, it is not going to create a problem. Okay, because it's come under secondary stresses. So because of these two reasons, we allow little bit higher so that we don't have to unnecessarily increase the thickness of a column, because wind and seismic are going to be really critical for the column. Okay, so for these two reasons, we try to code has permitted to allow the allowable stress 20% more than the normal. Okay, so that was the answer of the last question which I asked. And let us proceed with the column design, with buckling. Okay, how to design the column for buckling. Okay, now how buckling comes into picture. The buckling is buckling of a column happens due to excessive compressive load. Okay, like if you take a stick, okay, and at the both the ends, if you apply a lot of force, the stick will just bend. Okay, so that is called buckling of a column. It will buckle. Okay, it will not fail, it will not yield. Okay, that is the difference. Before yielding, it will buckle. So it will buckle at much lower point than yielding. Okay, so buckling will happen before yielding. So that is creating problem. We need to check for buckling. Just by checking the compressive stress will not work here. Okay, so again, how buckling is happening? Buckling is happening due to external pressure. Okay, like external pressure design we do. If you remember the external design pressure chapter, there we discussed about the buckling phenomena in detail, because external pressure causes buckling. And that is a really catastrophic failure. Without giving any indication, it will just collapse. Okay. So that is really critical. Now, how it is different in columns? Okay. One point is that in column, apart from external pressure, you can see there are lots of additional compressive loads, which we just saw in the previous part. There is compressive stresses due to wind or seismic. There is compressive stresses due to empty weight. Okay, so not only wind, or not only external pressure is causing a compressive stress, but apart from that, your wind, seismic, weight, all are contributing to the compressive stresses. So buckling chances of column is much higher than your normal pressure vessel. So how to do that? How to do that calculations? Okay. So that if you just follow 23B of ASME Section 8 Division 1, okay, I'll just project that. Okay. So if we just go to the buckling part of 23B, okay, step 1 is, it's very similar to what we do in external pressure. If you remember that, it will be much easier. So for external pressure calculation, what we did, we went to geometrical chart, and based on D by T, L by D ratio, we found factor A, which is a geometrical factor. Okay, from geometrical chart. In this, we don't have to go to any graph. Directly formula is available, which you can apply and find A. It depends upon the outside radius and divided by the thickness. Only these two parameters, radius and thickness. So with that, you will have factor A. And then, like we followed in external pressure, just follow the chart of that material, CS1, CS2, whatever is applicable. And then just follow the same procedure, go with factor A, whatever temperature line it is touching, move horizontal, and you will get factor B. Okay. And that factor B is actually the allowable compressive stress. Okay. So that is the maximum stress, compressive stress you can allow in a column. Okay. But now you'll ask that, okay, this factor B, just taking the outside radius and thickness into picture. Okay. It does not depend upon other compressive loads which are already there. Like I said, there is wind, there is seismic, there is a dead weight. Those are also actually contributing to the compressive stresses, but here we are not taking into account. So how to do that? So first of all, this B is your buckling pressure, which as per code you are calculating. Okay. Then if you see this, like I was explaining, there is external pressure, and at the same time, there is other compressive loads due to weight, wind, or seismic, right? Or any other bending moment. So there is compressive stress with that, and there is compressive stress due to external pressure. So buckling, the B value which we have calculated, that has taken care of this, the external pressure, right? But what about the other loads? How to deal with the other loads? How to compare, how to take care. Okay. So now how to take care of the buckling? So if you go to ASME section 8 division 1, the clause 23B, that gives the step for buckling calculation. That is actually, it calculates the maximum allowable compressive stress for that any of vertical column, or it may be even horizontal. Okay. So how it the philosophy of calculating buckling is same as calculation of external pressure. Okay. Because finally the buckling is happening due to excessive compressive stress, which is getting generated due to external pressure mainly. Okay. But now in column case, why it becomes critical, because there are other loads which are present and they are creating compressive stresses. Like we saw in the part 1, the dead weight also creates lots of compressive stress. There is wind or seismic. There are additional moments which are coming on that either nozzle or additional weight, eccentric weight which is there, that will also create some moment, and finally it will convert into stresses, and that will be tensile in one side, bending at one side. Okay. So there are lots of loads which are compressive in nature, and compressive load creates buckling. Okay, and buckling, your vessel or any part in buckling fails very catastrophically. Okay, it will not give you an indication. It is not going to yield. See, if yielding happens, it gives you lots of indication because yielding comes with deformation. You can see it. But in buckling, it will happen very catastrophically, immediate. There is no indication at all. Okay. So how to calculate buckling? So first of all, for pressure, that external pressure which is there, for that, what is the maximum allowable compressive stress, that we will see. And then we'll see how the effect of how to take the effect of other compressive loads. Okay, so the procedure is also similar to what we do for external pressure. We start with factor A. There we used to go to geometrical chart G, where we used to find that A value based on L by D and D by T ratio. Here directly there is formula available, which is based on outside radius divided by thickness. Okay, these two, thickness and outside radius, are the two factors based on which your A value is determined. Okay, once we have that A value, we'll go to material chart, applicable material chart for the material. There are different charts, CS1, CS2. For 516 grade 70, it will be CS2 chart. So we'll go to that applicable chart, move vertically with the factor A value, and then wherever that temperature line is touching, just move horizontal from there, and you get the B value. That V value is the maximum allowable compressive stress for your column. Okay, so that is that compressive stress is to take care of the external pressure. But what about other compressive loads which are there? That is not taken into account. So see, in this case, not only the compressive stress is due to external pressure, but also due to the weight and other loads like wind, seismic, or the other loads where bending moments, which are creating bending moments. Okay, so that buckling will be, the chances of buckling will be much higher. So how to check that? So for that, we do unity check unity stress. How we do that? We calculate all the combined compressive stresses like we did in part 1. We'll accumulate all the stresses which are creating a compressive stress in nature, and divide that with allowable compressive stress based on factor B, which we have got from 23B. Okay, multiplied with 20%, because that 20% higher allowable stress is permissible. So total combined compressive stresses divided by allowable compressive stress based on factor P increased by 20%, plus whatever axial stresses we are having, divide that with allowable external factor P. How different is this factor? Now you'll see that both are looking similar. Okay, but this allowable external factor B is the factor B calculated for external pressure. Okay, so the axial stress created by external pressure divided by the allowable, which is in this term, it's B value, which we get from calculating doing the calculation for external pressure. Okay, this B is different. The 23B, we just saw how we calculate the factor B based on 23B. This is based on 28. Okay, so if we divide these two, the ratio, the final addition of these should be less than 1. So if this is less than 1, then unity check is passed and we are good. So this is the actual buckling calculation for a column. It's very simple, isn't it? Once you understand, it becomes really simple. So first, find out what is the allowable compressive stress, and then do the unity check. These are the 2 steps to calculate buckling in a column. Okay. Now let us come to the second part, which is tall columns with 2 or more diameter. Okay, like you see in this figure, we have a column which is having different diameters. The diameter is lesser at the lower part. The diameter is more at the part which is upper. Okay. Do you think any difference will be there rather than designing a normal column in and compared to this column? Okay. Do you think anything? Just pause this video and think about it. Okay. Before going further, just pause and think what can be a different, why we are trying to discuss what is different in this 2 or more diameter vessel than your normal 1 diameter column. Okay. Okay. Now let us discuss that. Okay. I hope you have thought of it, and let us see if it is matching with your thinking, whatever you have thought, whether it is matching with what you thought. Okay. Great. So now let us see how what happens here. See, normally there will be a cone which will be connecting your larger diameter to the lower diameter. Okay, we don't have any other option. We'll have to provide a cone to join this. Okay. Now you see, we can put a simple cone without any knuckle or a flare, a simple cone, or we can have a knuckle and flare. Which one of these two you think is a good design? A simple cone or a cone with flare or knuckle? Okay, just think about it and then, okay. Great. So I hope you have thought about it, and see, if any part is changing its shape very immediately, suddenly there is cone and there is a straight shell which is coming. Definitely, if the parts are changing, there will be discontinuity stresses. Okay, and it will be very high if your part is changing very suddenly without any radius. So, and that is the reason to provide knuckle and flare is really good design. Okay, but then there is a catch also. Making this cone with flare and knuckle, it's not an easy job. Okay, it's really expensive to fabricate. This fabrication is not simple and it's not like it can be done by any vendor. It is really tricky fabrication, and you need expert fabricator to make this cone with knuckle and flare. Okay. So that is the challenge. It's good for design, but it is expensive. So there is always a trade-off. Okay. So normally we go with simple cone, but whenever the pressure is very high, okay, roughly you can take that value as a 20 bar. That is based on our experience. There is no code guideline for that. It comes under good engineering practice. Okay, so if pressure is more than 20 bar, we always try to go with knuckle and flare. Okay, you can even start earlier if you are convinced that your fabricator can do that. So with discussion of with your fabricator, you can even select for lower pressure also. Okay. So now if we are providing a knuckle or flare, what should be the radius? Okay, we have already studied in toriconical part what should be the radius. The same thing applies here also. It is minimum of 6% of the OD or 3 times thickness. Whatever is the minimum, that is the minimum knuckle or flare radius. Okay, if it becomes more, the forming becomes even more challenging. Okay, so you have to keep it minimum, closer to the minimum value, but definitely more than whatever code is given. Okay, so this is the second part. You have to provide cone, flare, and knuckles are preferred. And if you are providing cone and knuckle, this is the guideline to provide the radius. Okay. Then what is next? Whether that covers the 2 diameter part? No. If there is 2 diameter, if cone is coming, there are discontinuity stresses which are getting generated at these points. wherever you have change in diameter, there are discontinuity stresses, and you may be asked to calculate that. So you don't have to go for FEA in this case. There is a guideline mentioned in Bednar to how to calculate the discontinuity stresses at the cone and shell junction. Okay, and we are going to talk about that. So this is the area which is critical. Now, if we just enlarge that, these are the portions which we are going to talk about. The diameter change, which is the larger diameter, and the smaller diameter. Okay, these are the two places which we have to focus. Okay. Now, there are, just consider whatever at this portion, whatever is above that, there will be some weight which is exerted on this cone, right? At this section, we just focus on that. We are trying to find the end condition for designing this discontinuity. So whatever is coming above that, that is the weight we can use, and the moment which is getting created due to whatever loading we have, the moment which is getting created at this point, that is the moment we are talking about. Okay. Then if we just say M is the external moment, weight at the junction, D if we take as the diameter of the larger end, and T is the corroded shell thickness, then how we'll do the calculation? It will be PE, which is, first of all, we have to calculate the equivalent pressure. Okay. Because see, the chances of the failure here is more due to buckling. Okay. So we are trying to create additional pressure by using that moment and weight which is coming at this portion. We are trying to convert it into equivalent external pressure. Okay. So this is the formula which you can use to calculate the external pressure. Okay. So L here is this value 4m divided by pi d square. Okay. So this is actually the unit stress, okay, calculated due to bending moment and the weight. Okay. It's nothing more. It's a compressive stress, and it is just linearized by excluding the thickness. Okay. So a linear stress. Okay. So thickness is not coming into picture. If you just divide it by thickness, it will be the exact formula for calculating the compressive stresses. So based on this, we will get the equivalent external pressure. Okay. Now what to do with that? With using that equivalent external pressure, we will be able to calculate the stresses in cylindrical portion and also in the conical portion by using this formula given in Bednar. Okay. The formula may look complicated, but we can definitely simplify it. Okay. So this P we have already calculated. R is the radius, T is the thickness. So if we are talking about the larger part, the radius and thickness, and we are talking about the stresses in cylinder. Okay, we'll calculate the stresses in cone also. But first we are talking about the stresses in cylinder. Okay, so we'll use the diameter and thickness of the cylinder. Okay, so all these things are known. Now 0.5 plus minus x. The x is a coefficient. Okay, this value you will get in Bednar, and it depends upon the ratio of the thickness of the cone and shell. Okay, that is defined as n. That is the ratio of thickness of cone and the thickness of the cylinder. Based on that, your x value and also the alpha, the cone angle. So these two parameters, based on these two parameters, you can find this x value. So the tabular format, you just have to select that value and you will have this x, y, whatever coefficients are used. Those are just geometrical factors based on your thickness ratio of cone to shell and the conical angle alpha. Okay. So if this is also known, R by T again. So all these are now known, and now the equation looks really simple. Okay. So longitudinal stress will be given by this. We will also find the circumferential stress. So we have sigma L, we have circumferential stress, and then we can compare these to the allowable. Okay. Same thing we can do for the cone also. Cone at this junction, because the stresses in cylinder will be different, in cone it will be different. Okay. So if you see here, this n cos alpha is coming into picture, and this n is actually the ratio which I was talking about, the thickness ratio of the cone and shell. Okay. U and Y, you see here, that is tabulated in Bednar, and you can find that value. It depends upon thickness ratio and alpha. R by T is already known. So all these terms are known. We will be able to get the longitudinal stress at the larger diameter of the cone and the circumferential stress at the larger dia. So we have longitudinal and circumferential stress of cone. We have longitudinal and circumferential stress of cylinder. Okay. Same thing we can do for the smaller end also. Only you have to replace the radius and thickness of the smaller cylinder. All the formula remains same, that X and Y value will be also same, because they are also depend upon conical angle and the thickness ratio, which is same. Okay. If the thickness ratio, the thickness of the smaller diameter is different than your, the thickness ratio may change little. So you'll have to find a value for X and Y in this case. So longitudinal stresses at smaller dia in cylinder, circumferential stresses at smaller dia in cylinder. This is the formula, and the same thing is for cone also. So by using this formula and method, we will be able to find the discontinuity stresses at cone to shell junction. Okay. So you don't have to perform any FEA, just design by rule. We can find the discontinuity stress. Okay. Isn't it amazing? It's a really good formula which is there, and by which we can calculate discontinuity stress. Otherwise, we used to think that we only target the primary membrane stresses with design by rule, and we cannot calculate discontinuity stresses, but Bednar has given methodology to do that. Okay. So this is the end of part 2, guys.